Welcome to the 6th Shaw-IAU Workshop. My name is Giulia Perotti. I'm a junior group leader at the Max Planck Institute for Astronomy. And today I'll report on some observations obtained recently with the James Webb Space Telescope targeting a young planet-forming system. Right, so let's dive into the science. So planets, like the ones in our solar system, form in disks. These are complex structures that are composed by gas and interstellar dust. They are the ones that you can see here in this image. And well, the ones that you are seeing, they are really young compared to our solar system. They are about 1 million years old, and yet you can see some structures such as rings and gaps where planets may be forming. So what we are currently doing as a community is indeed to understand what are the physical and chemical conditions really early on at 1 million year, but also earlier stages, and to understand, therefore, how stars and planets are forming. In comparison, our solar system is significantly older, right? So it's 4.567 billion years old. So I really want to understand, go back in time and look at these structures, look at these protoplanetary disks to understand how our solar system formed in the first place. So planets are forming in disks, but it is really hard to see this formation in action, in the sense that, as you saw in the previous slide, there are several candidates that are showing these substructures, these rings and gaps, where planets may be forming, but currently there is only one system where we are unambiguously detecting not just one planet, but two planets in the act of forming. I'll talk really soon about that because this system is called PDS-70, and indeed it has been the target of the study that I led and I will present you today. So this is PDS-70. It's an extraordinary system. It's located fairly close by. It has, well, a central star, which is cooler compared to our sun. When our sun was young, the system is about 5.4 million years old. And around the star, there is some material that composes a so-called inner disk. At the same time, you see this really prominent and bright outer disk here that extends up to about 87 astronomical units. You see this gap that is particularly large, and it is, at least for this case, carved by two or more protoplanets, PDS-70b, discovered back in 2018, and PDS-70c, discovered 1 year later. Around PDS-70c, a circumplanetary disk has been detected. Therefore, a disk around a planet within a disk, basically at this location, exomoons like the ones around our Jupiter are currently forming. So you can have an idea just by looking at this beautiful ALMA image obtained in 2021, how great this system is to study planet formation, well, star and planet formation in action. But let us take a step back. Indeed, as I said, planet-forming disks are complicated structures. A lot of processes are taking place in these structures, for example, as they are composed by dust, micron-sized dust, sub-millimeter-sized dust, and also larger pebbles. When this dust is radially drifting towards the star, some of it accreting onto the star, some forming protoplanets, like in PDS-70. And at the same time, there are temperatures and density gradients in the disk, with the hottest regions being closer in and the coldest being like further out. Disks typically extend over hundreds of AU. And well, they're also characterized by snow lines or ice lines, which are the location at which specific molecules transfer from the solid to the gas. Particularly important is the water snow line, because this location, it is thought that most particular rocky planets form. What about the chemical composition in disks? It's really important to understand what is the chemistry in disks at different radii, in different regions from the star, to understand what is the composition, the final composition of the planets, or at least, well, the initial building blocks of the planets, both the bulk and, well, the planetary atmospheres. So far, about 70 chemical species have been detected in protoplanetary disks. This is a fairly low number. Consider that more than 300 chemical species have been detected in the interstellar medium. And, well, this is because disks are tiny regions in space, and this comes with observational challenges to probe the chemistry in there. So some of the molecules have been detected in the infrared. This plot is not updated anymore because JWST in these past 2 years has been increasing the number of molecules detected in the near and mid-infrared. A few have been detected in the far infrared, in particular, well, with Herschel, but the largest majority has been detected at some millimeter wavelengths, in particular using radio interferometers such as the some-millimeter array, NOEMA, and the Atacama large some-millimeter array. So basically, it's really important to study disks using different facilities that operate at different wavelengths, because depending on the wavelength we are looking at a particular system, a particular disk, we're obtaining different constraints. For example, you see a cartoon of a disk, and you see that if, for example, we use ALMA, radio interferometer located in Chile in the Atacama Desert, these are 66 radio antennas. If you use this instrument to look at the PDS-70 system, for example, that I just introduced you, you can obtain information about dust continuum, so the composition of some millimeter size dust. We can also have information about the gas located in disks, but we are mostly probing fairly cold gas that is located in the outer part of the disk, and therefore like below 10 AU. On the other hand, if we are using JWST, when we're using JWST, we are probing the really hot gas located in the innermost disk regions, so below 10 AU. With NIRSPAC, we can go really close into the star till about 0.1 astronomical units from the central star. So using both MIRI and near-infrared, we can really probe the hot gas in disks that are not highly inclined. We can also probe the ices, the solid-state material, in nearby disks that are edge-on, that have an inclination above, well, close to 90 degrees. And therefore, it's really a particular region to study because the temperatures are much higher, being closer to the star. And in this range, several key planet formation tracers and key molecules for the emergence of life strongly emit. Let's dive very quickly into JWST. I will not go into detail because several other talks will dive into the instrument. Here, I just wanted to flash one slide showing that compared to previous space observatories, in particular Spitzer, that operated in the infrared, JWST has a significantly larger area, larger primary mirror, 6.6 meters compared to Spitzer, that was 0.85, and ISO, that is not on this slide, it's even smaller. So this difference in primary mirror diameter results in a significantly higher, significantly greater sensitivity, and well, namely 45 times greater sensitivity compared to previous missions. We'll see in a minute what that results when it comes to the analysis of spectra. So what do we observe with JWST, in particular the mirroring instrument that I've been using together with my team? One of the key molecules to observe that strongly emits in the mid-infrared wavelength range, and in particular in the mirroring range that goes from 4.9 up to 28 microns. Well, it's water, which is a key molecule for planet formation and also for life as we know it on planet Earth. You see an animation, like spectrum, that shows one of the modes of water, and you see that this movement, the modes of this molecule result in several lines, several transitions here throughout the wavelength range of MIRI that I just mentioned. And study the water molecule in particular, and the shape and the flux of the water spectrum is really important for us to understand what are the disk properties. For example, if a disk is really hot, then we would have a higher flux of water lines, of water transitions here in red, whereas if we have a cold disk, then we would have less transitions and also several, in particular in the vicinity of the star, significantly lower flux. The observations that I will show you in a minute, the results that I will talk about next, are part of a large program, a large consortium that is called MIRI, Mid-Infrared Disk Survey, or MINDS. This is a GTO program. It means that it is a guaranteed observing time program of about 120 hours that involved hundreds of people in designing the instrument, building the MIRI instrument, and later on commissioning it after the successful launch of Webb, and developing the tools for the data analysis and for the interpretation. So with this slide, I really want to thank everyone in the team that allowed me to work on some of the really first JWST data of planet-forming disks and present these results here. Right, so this is how the spectrum of the PDS-70 system, in particular of the inner disk, looks like. And what you can see is that we have really broad features. Some of them, are dust features, for example. This one here, these are silicates. But I was myself really interested in the gas. I wanted to see whether there was some gas, an inner disk gas reservoir right there in the region where rocky planets form, below 10 AU. And therefore, as soon as we were satisfied with the data reduction, I zoom into the 7 micron region, and instead of just seeing noise, I was really happy to indeed see lines, some lines to analyze. Just to give you an idea, this is what we had before JWST, pre-JWST times with Spitzer, a spectrum that it was not possible to decipher when it comes to the gas composition. And now this is what I saw when zooming in onto the Webb data in white. You see all these clear lines here that then were compared to a model. And you see now the model in blue and the JWST spectrum in white, and all these transitions here are water, vapor water, that has a temperature of about 600 Kelvin, so pretty hot water, and a fairly abundant reservoir in this inner disk that we initially thought to be dry. So this is the first time that we're detecting water vapor in a disk where two exoplanets are known to be forming, which is really great because it can really allow us to study what are the composition of the rocky planet forming zone at a time where planet formation is in action. So why the detection of water in this particular system and in this particular region of this disk is so important? This is because the classic picture is that of the inner disk where rocky planets are forming is a dry region compared to the outer disk where gas giants are forming. So you would have to plug into this cartoon our solar system. Indeed, would have the inner disk really close to the star, being devoid of water vapor, and of dust material. Of ices, water ice surrounding the dust, compared to the outer disk that is rich in water ice. But the first detection of water in this system that hosts planets and is 5.5 million years old tells us that indeed inner potential rocky planets forming in the system have access to a water reservoir. Now, how much water is in there? Of course, this measurement has to be done over multiple wavelengths, not only with one instrument, but if you would have to extract just simply how many molecules of water vapor are in this spectral region, which is really tiny, from 6.8, give or take, until 7.4, then that would boil down to basically one North Sea. In reality, again, this analysis has to be done over the full meter wavelength and also include the instruments, include the results for many more instruments. So these are open questions for the future to us to answer. What is the total amount of water in PDS 70? We recently awarded other observational time to dive into this question. And at the same time, we can start proposing what is the origin of water in the rocky planet forming zone of PDS 70 based on the data that we currently have. So let's look at the geometry first. PDS 70 is not a compact disk, a continuous disk. It's not a disk that has small gaps or small rings, but indeed, as you can see from this slide, it has a really large 54 AAU gap. It has a low mass accretion rate, 10 to the minus 10 solar masses per year. This means that the star is not accreting so much material anymore. At the same time, this large gap, we know, being dust and gas depleted. So why do we pick up this water signal? Why the inner disk is still rich in water? So it could be that we are looking at an older reservoir that it is slowly consuming. So water was present in the inner disk in the form of ice pebbles when there was no gap. And then after the formation of the gap, the water from the inner disk was preserved. And this is what we are picking up today. So time will tell, but of course, this could be a valuable option. And therefore that, although the star is still fairly young, we are simply picking up an older reservoir preserved since before the formation of the gap. On the other hand, we know that this gap is gas depleted and dust depleted, but is not completely empty. This information we obtain from other facilities such as ALMA. And therefore, if gas is able to filter from the outer disk, where a lot of material, a lot of dust and gas are still present, to the inner disk, then if oxygen-rich gas populates the inner disk, then via the reaction that you see here on this slide, via two sequences of hydrogenation, we can form water. And we know that water is a UV absorber, and it's a molecule that can shield, act as a blanket, shield other water molecules from being fragmented, or in technical terms, photodissociated. At the same time, if gas is still filtering from the outer to the inner disk, at the same time also small dust particles that are micron in size, so we're talking about a dimension that is smaller than our hair, then, well, we'll have the inner disk populated not only by oxygen-rich gas, so we'll have not only gas phase synthesis of water vapor, but at the same time, simple transition phase from the water ice that you see depicted here in blue to water gas. So this discovery only makes us more excited for those still to come, for understanding the water evolution in this system, and then compare it to what we know about water delivery on Earth. For concluding, I want to thank all the thousands of engineers, technicians, and scientists that dedicated so many years to building JWST, and also gave all of us, including me, a really big present to work on this beautiful data set and living these exciting times of discoveries. And with that, I would like to thank you all for your attention, and you are able to contact me at any time, reach me for any questions you may have. Thank you very much.